For the Building Energy Spatial Data Interoperability task, Ecere provided a deployment of its GNOSIS Map Server as a geospatial and building energy data service. A 3D buildings dataset of Montreal accessible through OGC API Standards was loaded on the server and augmented with on-the-fly building energy calculations for buildings of interest from a processing API. In order to load the CityGML dataset of Montreal 3D buildings, integrating data from the City of Montreal, prepared by the Steinweiss Consortium, new capabilities to import CityGML data into the native GNOSIS data store were developed. The 3D geometry from buildings is internally stored in Ecere's E3D 3D model format. Reference points are stored in vector tiles using the GNOSIS Map Tiles format, whereas attributes are preserved in a SQLite database. The attributes present in the CityGML dataset itself included the neighborhood, building function, and year of construction. The deployed GNOSIS Map Server provides access to the 3D buildings dataset using multiple OGC API standards, including 3D geovolumes, features, and tiles. The 3D data can be accessed either through a 3D tiles tileset as per the core bounding volume hierarchy conformance class of the geovolumes, or as implicit tiles, which also correspond to the tiles API request for a given 2D tile matrix set. The 3D buildings dataset is shown here displayed in the Cesium client. Tiles of batched 3D models for an implicit tile can be retrieved either as 3D tiles batched 3D models, as binary GLTF 2.0, or as E3D models. It is also possible to retrieve vector tiles of the reference points georeferencing individual 3D models, and download each model independently as a GLTF or E3D model. The vector tiles are available as Mapbox vector tiles, GeoJSON, as well as GNOSIS map tiles. The same reference points are also available as OGC API features, including the original CityGML attributes, as well as a model identifier to request the corresponding building 3D model. Support was also added for including the unique identifiers within the 3D model's nodes, whether retrieving buildings individually or batched, providing a mechanism to retrieve the corresponding attributes using OGC API features. The virtual collection was also deployed, augmenting a subset of the Montreal buildings dataset for l'Île d'Ecere with building energy calculations performed on demand for an area of interest. This is achieved by submitting computation requests to the SimStat heating demand OGC API processes implementation developed by Steinweiss. The virtual collection leverages the OGC API processes Part 3 workflows and chaining extension. With the help of a GNOSIS Map Server adapter process acting as a processes Part 1 core client, the building energy computation output can be integrated within a processing workflow defined using the Part 3 extension, with processing triggered for an area of interest as a result of a data access request. An additional add attributes process is used in this workflow to combine the attributes from the energy calculations with the original CityGML building data features dataset by joining the two feature collections based on a common unique identifier. Here we can see the resulting dataset augmented with the new attributes, including the heated volume, the heating requirements for each month of the year, and more. In summary, OGC API standards provide interoperable and efficient mechanisms to stream 3D buildings datasets, and building energy calculation workflows based on OGC API processes and a Part 3 extension for workflows and chaining could be driven by 3D visualization clients, triggering on-the-fly calculations for the buildings of interest. With caching and optimizations, this energy calculation workflow could possibly even be integrated directly with workflows generating the 3D buildings dataset on demand, for example, for the latest available high-resolution and oblique satellite imagery.